Let's do a weak base problem. We talked about weak bases yesterday, right? Because we had to, because we said that a buffer is a weak acid in its conjugate base or is a weak base in its conjugate acid. So we had to talk about weak bases a little bit. We said most of those weak bases are organic in nature and they contain an amine functional group. And an amine is just a nitrogen containing compound. We're going to keep it super duper simple. And nitrogens are wonderful bases because they're great Lewis bases. They always have a lone pair unless they got a positive formal charge on themselves. They've always got a lone pair, and that lone pair can be donated, and that's great. Now, because y'all haven't taken organic chemistry, we can really simplify this. So instead of writing the crazy formulas, the organic formulas for most of these amines, we just call it B, right, for base. So we can, when you got to write that balanced equation, dissociation equation, right? Usually when it's a weak base, I'm just writing B plus liquid water. That's important because the water's not going to go in the mass action expression. And then what happens? Well, the base steals a hydrogen from the water. You get the conjugate acid HB plus, and then you get hydroxide because if we steal a hydrogen off the water, the electrons are making that bond between hydrogen and oxygen go back on the oxygen, you get hydroxide. So here is your generic equation for the dissociation of a weak base in water. And that's going to be really important, which means we can write always a generic mass action expression. Okay, now we call it a Kb for base dissociation constant, and that's going to be the Hb plus concentration times the hydroxide concentration divided by the original base concentration. So there is the Kb mass action expression. So with that in mind, let's work one of these problems. What is the hydroxide concentration and the pH of a 12 molar aniline solution? So in this problem, I just stole this chart right here out of an old textbook. You can look up the Kb value of aniline. It's right here. So the Kb value of aniline is 3.9 times 10 to the negative 10th. So I'm going to steal some of this information here off the board. So we got hydroxide ion concentration, end of the day. That's what we want. We want the pH of the solution as well. And we have an initial base concentration of 12.0 molar. And I'm going to steal that Kb of aniline out of the chart. And that's 3.9 times 10 to the negative 10th. So not a super good weak base. It's pretty darn weak. Now, here's the beautiful thing. Here's what I'm trying to tell you. You don't have to write this equation right here. Okay, when you see that it's a weak base problem, just leave it as B plus H2O goes to HB plus hydroxide. And what you have is that initial aniline concentration, initial concentration of B. So here's what we got to do. We got to make an ice table. So again, equation, mass action expression. What comes next? Ice table. So we're going to make an ice table. So there's our ice table. Now we plug this stuff into the mass action expression, plug in Kb, see if you can make the x a small assumption, and solve for x. Once you get x, x is the hydroxide. So you'll have one of the pieces of the puzzle. And then once you get the hydroxide, think about how you can get to the pH. So I'm going to give you 2 minutes. I'm going to let you try to finish this problem out, right? So let's plug it in. Here's the Kb value. See if you can't get x. See if you can't get me a pH. Go ahead. All right, rock and roll. So here we go. Man, I'm kind of out of room. I'm gonna do it down here. 3.9 times 10 to the negative 10th equals x times x over 12.0 minus x We want to see if we can get rid of that minus x, and we can. If we take the smallest initial concentration, 12.0, and we divide by the constant 3.9 times 10 to the negative 10th, you get a number way greater than 500, folks. X is small. You can get rid of the minus x, multiply both sides by 12. We get 4.7 times 10 to the negative 9th equals x squared. Take the square root of that, and we get x equals 6.8. I'm going to go with 2 sig figs because of the base dissociation constant, Kb value. 6.8 times 10 to the negative 5th. So that's my hydroxide ion concentration, which was the first thing that this was asking for, right? Well, there we go. And now it wants the pH, and this is the only thing that makes a weak base problem a little harder than a weak acid problem. If this was a weak acid problem, X would be your H plus ion concentration, negative log H plus is pH. But in a weak base problem, X is your hydroxide ion concentration. So what do we do? Well, you got two options. You could use H plus times OH minus equals KW, which is 1 times 10 negative 14th, solve for H plus, and then take the negative log. I personally don't do that. What I do is I take my OH minus ion concentration, get a POH, and then remember, pH plus POH has to equal 14. So 14 minus the POH gets us the pH, right? So my POH is the negative log of that hydroxide ion concentration. So 6, or yes, 6. So 4.17 is my POH, and then 14 minus that, 14 minus 4.17 is 9.83. Always good when you're done, when you're doing a weak base problem and you get a basic pH as your final answer. That's always a good feeling. pH is 9.83. So weak base problems, not really different than a weak acid problem. Only you could maybe make the argument that they're slightly more difficult, but that's only because you get a hydroxide instead of an H plus, and usually they're asking for pH.